can start this second session. Our first speaker is Professor Saberi. He will talk about networks of perfect tensors and symplectic geometry or finite fields. Please.
Great. So thank you very much for the introduction. I'd also like to thank the organizers, especially Ryutakanagi and Wilson Zuniga, for doing so much work to put this together. I'm going to tell you a little bit about some ideas. It's a little bit of a grab bag, I think, this talk, but there'll be various ideas that in my mind are close to p-Adic ADS-CFT or close to things that got me thinking about p-Adic ADS-CFT. In the first place, maybe I should say this is joint work with collaborators. So the paper is with Matilda Marcoli and Matt Heidemann. And I also wanted to make reference, I think it's appropriate to just remember briefly Steve Gubser. So Steve was clearly a great physicist of the very highest quality, died a couple of summers ago now in a climbing accident. And he was a great, he did a lot of work on p-Adic ADS-CFT and was really a strong advocate for it. So I wanted to just remember him briefly here. So what are some of the main themes of this talk? The main theme is that sort of arithmetic and constructions come up in physics in lots of surprising ways. Or seem to come up. That's kind of a main theme of the whole conference. I was really led to this by thinking about the ADS-CFT course, which is a thing that I seem to always work adjacent to, but never directly on. So I'll tell you a little bit about that. We got a nice reminder already in Leanne's talk, but I'll sort of give my perspective on that. And then I'll say a little bit about tensor network models. Again, from my sort of very biased perspective. So I think these were very popular and still are popular as discrete models that have at least some features of the ADS-CFT correspondence. There's ways in which they're satisfying and some ways in which they're not. And p-Adic ADS-CFT was, at the beginning, I think, about trying to rectify some of the unsatisfying things. And say just a bit about p-Adic ADS-CFT. I should put the word perfect here. So that's a specific class of tensor network model, which has showed up in sort of holographic tensor network models, in particular in work of Preskel and collaborators. So I'll remind you how that goes. I'll say a few things about p-Adic ADS-CFT. And then sort of another open question. In my mind, there were models that Preskel, I'll describe what they are in just a moment. One question was about what the natural discrete geometry is for such a network model that doesn't break symmetries. And many people are very familiar. There are nice examples of p-Adic symmetric spaces that are discrete. And so it's natural to try and build discrete models of the ADS-CFT correspondence that are somehow based on those symmetric spaces and on p-Adic groups. But the other ingredient that goes into these models is a specific choice of tensor, or just really it's a finite dimensional, an element in a finite dimensional vector space, the tensor. And I sort of gave a bit of thought to what that might mean physically. And it's kind of interesting, or I was very surprised by it. There's a really natural way of thinking about where this perfect condition comes from, or how such things are constructed in terms of finite fields. And this again feels very suspicious because there's a sense in which the vertices of the Ryutakanagi tree are decorated with the residue field of the p-Adic field, which is some finite field. So I'll tell you a little bit about how I came to think about this, and then perhaps say some words about how I hope that it will all fit together at the end. And you should feel free to ask questions, of course, at any point. So that's a rough plan of the talk. Let me start with a couple of generalities. So of course originates in string theory. And in string theory, it starts as a duality between two things that are relatively complicated. So on one side, you have what's called equals 4 super Yang-Mills theory. And on the other side, you have type 2 supergravity. On a hyperbolic space, ADS5, the product of a hyperbolic space with a positively curved space, which is just the 5 sphere. Here the gauge group is UN. And here there are n units of what's called 5-form flux. This is not so important. There were sort of two things at the beginning. This very concrete example, which involves these rather intricate ingredients or pairs of dual theories. There was another way which was more sort of bottom up, which had to do with Witten, or I think of Witten's, there are sort of 3 original papers on ADS-CFT, one by Steve Gubser with Klebanov and Polyakov, and one by Maldacena, and one by Witten at the same time. And I think of Witten's paper as being the more bottom up among these papers. So it talks about if there is to be such, why could one expect there to be such a correspondence, and what are the geometric ingredients that would have to go into it? And those geometric ingredients are all of a sudden fairly simple. I imagine that I think about, there's always 2 sides, called boundary and bulk. Here I have some theory which lives on the n sphere. And here I have a theory which is on a hyperbolic disk of dimension n+1, whose boundary is that n sphere. And it's the fact that conformal transformations in dimension n, the group of conformal transformations is isomorphic to the group of isometries of this hyperbolic disk. And that means, in a sense, so the fields in this bulk theory, whatever it is, they form representations of that isometry group, which is the sort of generalization of the affine group or Poincare group that's appropriate for negatively curved space. And that just happens to agree with the group of conformal transformation in the lower dimensional thing. And that's where the operators of a conformal field theory should form irreducible representations of that group. And so one expects that there's a correspondence between operators in the boundary and fields in the bulk. And this fact that operators correspond to fields is related to, well, I won't say anything about this. This is work of Costello. together with some combination of Lee and Natalie Paquette. So, as a footnote. The other interesting thing that happens is that the theory in the bulk is always a gravitational theory. So string theory is some enhancement of a theory of gravity, if you want to think about it that way. And here we have conformal field theory without gravity. So in a sense, this correspondence is very nice because it tells us that two things correspond, one of which we don't really understand very well at all. Quantum gravity is notoriously difficult. And this gives us a way of trying to ask questions or do computations in what we believe should be a theory of quantum gravity by asking questions about conformal field theory. And another advantage of this duality is that it's sort of a strong, weak duality. So for example, questions about strongly coupled CFT, which are hard to resolve, become sort of weak coupling questions on the other side, and they can be asked just in the language of geometry or classical gravity. So there's just a few sort of generalities about the way one might think about the ADS-CFT correspondence. There's a huge dictionary, of course, of quantities that one computes, both on the bulk and the boundary, and the ways in which they correspond. There are many, many thousands of papers doing these kinds of correspondences. But one main sort of commonality or theme in the development of this dictionary has been entangled, especially recently. And there's a shadow of holography right away. So if you think about the Bekenstein-Hawking formula, which tells you about the entropy of a black hole, this tells you that black hole entropy goes like the area of the event horizon divided by some number. Depends on units and conventions. The point is that these things are proportional. And this tells you that degrees of freedom in quantum gravity scale strangely. If you think about a typical quantum field theory, a quantum field theory is like a bunch of local degrees of freedom, like a harmonic oscillator at every point in space, if you will. And so the number of degrees of freedom inside of some box is proportional to the volume of that box, because that's how many different local degrees of freedom are in a field inside of there, almost by definition. In quantum gravity, it seems not to work this way. So the event horizon of the black hole, you can think of as having traced out some region that's a box where I can't make any measurements as to what's going on inside of it. And so the entropy of the black hole is measuring the number of possible things that could be going on inside of this box that I can't see. But the number of microstates is somehow proportional to, it scales with the area of the event horizon rather than with the enclosed volume. And that's a sign that there are many fewer microstates in a theory of quantum gravity than you'd expect. It behaves like a field theory one dimension lower. So that's another piece of evidence for a proposal of this kind, right? This sort of scaling in theory of quantum gravity is appropriate for a field theory, but in the wrong dimension. So there's a big generalization of this. Which is called the Ryutakanagi Formula. Sorry, question? Maybe not. Okay. So how does this, what is this formula saying? If I were to draw a picture of it. My conformal field theory here living at the boundary of some space-time where the quantum gravity theory lives. And so quantum gravity is extending out here into the bulk. If I think about a fixed time hypersurface in this conformal field theory, I can associate a Hilbert space to that, just thinking about quantizing a field theory. So the Hilbert space always lives in codimension 1. And you could ask, if I have some region of that space which is inaccessible to me, like what's behind the event horizon of the black hole, call that area A, and I trace out A, then there's an entanglement entropy SA. And what the Ryutakanagi formula says is that SA is proportional to, this is now a field theory entropy, surface gamma A in the bulk. So here I think of my theories on the boundary. There's some hyperbolic space sticking out of it. Surface gamma A. And there's a very similar looking formula, which says that the bulk geometry is telling me about entanglement properties of a state in this CFT. Probably it's the ground state. And so this is coming back to a theme which was already in Lin Yang's talk in a big way. Entanglement, something about the ground state, telling you geometry of the bulk. And so it's natural to ask, how can we build or think about it's sort of a natural question to ask. What I mean by like, of course, every state in a Hilbert space, every Hilbert space is the same if it's separable, and every state is related by a unitary transformation to every other state. So be careful about what one means when one says a state has properties. But these properties have to do with locality. So really it means that the Hilbert space is thought of as constructed from tensor factors, where those tensor factors are labeled by the geometry of this space. And it's with respect to that tensor product decomposition that it has meaning to say this state is very entangled, this is not very entangled. It has to do with the basis of things that are decomposable with respect to the position basis, if you want. The tensor product decomposition coming from the geometry of this time where this thing lives. So that's why asking a question about a specific vector in the Hilbert space is not boring. This is a Hilbert space equipped with lots of other structure, in particular, like a very intricate and geometrically determined tensor product decomposition. And a way of building such states is to sort of take that tensor product decomposition seriously and to model Hilbert as a limit of tensor products of finite dimensional Hilbert spaces that are just literally tensored together. And so that leads you sort of to the idea of a tensor network. So there are many versions of these. There's a whole literature just on tensor networks. I'll just discuss one example. And that's due to, I believe, Harlow, Preskel, Stowski, and Yoshida. Paper maybe 5 or 6 years ago, I'm not entirely sure. And they define, so they begin by fixing a finite dimensional Hilbert space once and for all. And you view that as sort of the fundamental chunk out of which everything is pieced together. I'll call it V. Then I choose a perfect tensor. What is a perfect tensor? Well, it's an element in the dth tensor power of V. So psi is perfect. When as a map, I can always, because V is a Hilbert space, I can always view it as a map from V tensor K to V tensor D minus K. And if I take K to be less than or equal to D over 2, it's always an isometric embedding. So roughly speaking, that means that this element is very, very far from being decomposable with respect to this tensor product basis. It has the largest possible rank. And then it's also kind of uniform in the sense that it preserves the natural metric, right? The Hilbert inner product. It turns out that it's actually sufficient if D is even, you can just require that for any partition of the indices into two groups, psi is always a unitary transformation. So full rank invertible unitary transformation. That's sufficient to guarantee this property, but this is, to me, the more natural definition. So then I can sort of pick any tiling, and I'll be intentionally vague about what this means, of any geometry whatsoever. You decorate each tile with this same object, and you include, which means contracting indices along common faces. So that's how you build such a thing. And it's sort of natural in the sense that the condition that psi be perfect is totally local, right? So now I've given you a way of, given any geometry whatsoever, you know how to associate a tensor network to it, and that tensor network looks locally the same everywhere. So that's similar to notions of locality or isotropy that you would expect in a field theory. Of course, this is not as detailed of a gadget as a field theory, but it at least has that similarity. And you can expect that the geometry of the way these tensors are contracted is therefore reflected in the sort of output of this tensor network. So what's nice about this? Well, the normal surface property is actually obvious. What's that? Imagine if I have I'm considering the state which is associated to external legs. And now I take some region of this tiling. And that's the region I was calling A before. And I want to imagine tracing A out and asking what's the entanglement entropy of what remains. Well, I can visualize that partial trace that if I think about density matrices, that just means contracting a copy of A with a copy of A and letting the two copies of A complement stick out. Then sorry, question?
Ok, tu dis que tu n'as rien compris au papier que je t'ai envoyé. Hein? C'est la même chose. Ok. Oui. Oui, j'ai annulé le cours. Peut-être même le cours n'est plus là.
So perhaps mute.
Donc, dis-lui ça de joindre une autre section s'il peut, quoi.
Sorry, please turn off the microphone.
Ok.
Thank you. So how does one construct the reduced density matrix? One simply takes of A and contracts them together. Of course, I can view the tensor network as just giving me a map from the Hilbert space of A complement to the Hilbert space of A. And when I contract A with A, I've taken the partial trace, I get an endomorphism of the Hilbert space of A complement, and that's the reduced density matrix. How do I compute the rank of that matrix? Well, the rank is, in a sense, just the narrowest point. These maps can always be factored into projections and inclusions, which are isometric. So at the end of the day, all I've done is project onto the smallest Hilbert space I have to go through and then include into whatever larger Hilbert space. So that means that the entanglement entropy is like the dimension of the smallest log, I guess. And it's clear that that's the matrix. So this perfectness property is something that somehow forces the tensor network state to reflect the geometry in the way that you want it to, even though it's a purely local property. It knows nothing about geometry. It's reminiscent, I think, of, local differential equations that, like the geodesic equation is also local, right? Things like that. So somehow that's a sign that being perfect is an interesting property for a tensor to have. And I'll return to that in a little bit. So maybe just to put in a small footnote. So it was kind of the excitement about such models, which, there was a lot of many papers being written. And it was this wave of excitement that got me thinking about ways to discretize ADS-CFT. There was a lot of speculation about the fact that a tensor network looks like a discretization of the bulk space. And that the entanglement, which is at long ranges in this large distance entanglement in this Hilbert space state that you're constructing, is sort of constructed layer by layer by going farther and farther out into the bulk. And so this additional direction in this tensor network, the bulk direction, looks like a length scale, or equivalently an energy scale from the point of view of the boundary. So there was a lot of speculation about how the tensor network might be a bulk model of ADS-CFT. And what was sort of dissatisfying to me about this, or what I felt maybe deserved a better answer, was the question of how do symmetries play a role? Because this, I've chosen now just a very random tiling, could have been any tiling. It's not at all clear how the matching of symmetries between the boundary and the bulk survives here. Of course, I'm reproducing correct features of a piece of the ADS-CFT correspondence, namely this CFT vacuum state. But I seem to have, by doing so, broken a lot of the things that made me want to believe in such a correspondence in the first place. As many people know well, I won't dwell on this a long time, but there's a sort of natural discretization of what I'll call bulk boundary geometry. Which is via p-Adics symmetric spaces. So what happens there? Well, you've got, again, this sort of same diagram I've been writing with boundary and bulk. The boundary is the projective line over P, which is the boundary of the Brouhat-Titz tree, which is the symmetric space of lattices, rank 2 lattices. And the group, I was calling it isomorphisms here, and conformal transformations here. Of course, most of these transformations, but this is PGL to QP. And there are really, really nice stories that come out of this. We heard, I think, quite a bit about it already in the first talk. And there may be more about it. I believe Sarthak is talking at some point, so there will probably be some more about it. The p-Adics sort of capture very nicely most of the locality properties, so translation invariance, affine invariance, a notion of distance. Those are all present. And those are, in my mind, all of the things that make field theory special. On the face of it, field theory is many-body quantum mechanics, which is just something about a big Hilbert space and some states in it. Things start to get interesting when that becomes local, or especially invariant under symmetries, when it's connected to geometry or parameterized by geometry. And their geometry means having a notion, so locality means having a notion of distance, geometry means having a notion of, for example, affine transformations. And in the p-Adic world, all these things are just available. But the discreteness of the norm gives you sort of a discrete flavor which shows up over and over again, in particular in the discreteness bulk space, the Brouhat-Titz tree. And there are lots of wonderful results, which I won't really discuss today, which suggest that if I formulate field theories over places in a uniform way, and I write down, for example, the ON model, either on Rn or on QP to the n, in a way that's appropriately uniform, then results results of calculations in these quantum field theories are actually independent of place, in the sense that they are just some universal expressions in terms of special functions which are also naturally associated to each place. So this is really like to my mind, a very profitable and nice way of thinking about the problem. And I think, in this audience, I want to convince you. But I'd like to sort of carry along this notion of the tensor network for a moment and think a bit about the geometry of TP itself. So TP is, of course, a tree. So if you use 2, it would look something like this, of course, extended everywhere in all directions. And there's already a sort of hyperbolic, there's a notion here which is very much like the Ryutakanagi formula, which is that if I think about the notion of p-Adic distance, p-Adic distance is naturally connected to height. And so the measure of an open interval, the measure of an open ball in the boundary is naturally connected to the length of a geodesic that, so to speak, encloses it. So even the very construction of the p-Adic distance on P1 of Kp can be thought of geometrically in terms of bulk geodesics, and that has a very Ryutakanagi flavor. But there's a slight problem to thinking about perfect tensors in this setting, which is that you want the length of this geodesic, with the number of bonds along this geodesic, to be connected to the entropy. And with perfect tensors, you sort of add a dimension to your minimal Hilbert space whenever you cut a contraction. So in a sense, I want to build a perfect tensor network where bonds are contracted across the edges of the across the edges of the tree. And that means that sort of the natural geometry for a tensor network, if we're going to use this magical property that I talked about before to try to capture what's going on here, is that we would need it to live on sort of a planar dual to the tree rather than on the tree itself. So bear that in mind. I'm now going to move to talk a little bit about the property of being perfect. And then if I have time at the end, I'll come back to this. So this notion of perfect, you should suspect that maybe there's something physical hidden behind it. So we just chose it so that these computations were easy, right? It did a thing where it made the proof of the Ryutakanagi formula, proof of the Ryutakanagi formula for a state that's constructed in that way. It just made it obvious. I actually didn't have to compute anything. But that should tell you, if perfectness was the only local condition that I imposed, and it meant that what came out satisfied a formula that I want to believe has physical meaning, then that local condition should also have some physical meaning, or it should be related to the sorts of local data that I write down. in physical theories, because I expect them to also have the same formula fall out in a local way. And so it's kind of a nagging question, what is perfect, a physically natural thing to think about other than that it has this property? So here's my idea. Which is to think about the finite dimensional Hilbert space that I started with. So there are natural ways to get a finite dimensional Hilbert space by quantization. If V is the quantization of a phase space, it must be compact. Write down compact manifolds, even CP1 is an example where you can quantize that with appropriate additional data and get any finite dimensional Hilbert space out. That's kind of the representation theory of SE2 in the geometric quantization world. But I want to think about V a little differently. Because CP1, of course, is curved, and I'd rather think about flat phase spaces for the sake of ease. In fact, there's a way to get something like quantization by taking V to be the functions on any finite field. I guess I could write Q here. Let me write Q. So there's a very precise sense in which if I take a two-dimensional symplectic vector space over FQ, the normal story about representations of the Heisenberg group or about choosing a polarization and constructing the Hilbert space in quantum mechanics, that goes through perfectly well over another field. And so if I just study operators, it's natural to think of those as being the Heisenberg group associated to this symplectic vector space. That just means that there are canonical commutation relations. This is some finite group. In fact, it looks, it's a central extension. So it looks like this. And those act naturally on V. And in fact, V is the unique irreducible representation of this group whose central character is non-trivial. And part of the reason to maybe think about this is that, again, in the context of the tree, it's natural to think of copies of finite fields as floating around everywhere. The residue field is a finite field. But from my perspective, it's just also pleasant to see that something which looks exactly like, in fact, is formally exactly like canonical quantization, can give rise to a finite dimensional Hilbert space in this way. Move it. I believe it's 50 minutes, right? So I should end quite soon.
You have about 10 minutes, let's say. Since 10 minutes is
10 minutes,
for discussion.
Okay, so I'll try not to run too far into the discussion. So there's a very nice notion, right? So there's a dream that people have about quantization. It might be a functor from Weinstein's symplectic category to linear category. This is sort of the structure that's hidden behind a lot of what we hope is true about quantization. What do I mean by Weinstein's category? I mean symplectic manifolds are the objects, and the morphisms are Lagrangian correspondences. Unfortunately, this is really not true at all. In fact, Weinstein's category doesn't even really exist. There are problems defining compositions of morphisms, lots of technical difficulties, and even saying what this category should mean. Recent work by Verheim and Woodward. Trying to define what that category ought to be over the real numbers. But even if you could define it, you still don't expect quantization to be a functor, really, in the standard case. But there are two things that happen which make you sort of happy in this very simple example. One is that there is a linear Weinstein category. So that means symplectic vector spaces. And linear Lagrangian correspondences. And in fact, category is defined over any field, and over finite fields, there's even a quantization functor. This is surprising. This is work of Grivich and Hadani. So they define this for a category whose objects are symplectic vector spaces over a finite field and whose morphisms are symplectomorphisms. But there's a mild generalization which shows that this in fact works for general linear Lagrangian correspondences. What is a perfect tensor? We're now free to think semi-classically about it because we have a functor that says, given this algebraic, in fact, linear algebraic object over a finite field, it just becomes some tensor. I should say that this functor is nice in the sense that it carries direct tensor products, it carries symplectic duals to duals, and it behaves well under symplectic reduction. So it really has every nice property you could hope for. And this is better than the real setting. Perhaps because finite groups are nice, I don't really know. So what is a perfect tensor? It's just a Lagrangian subspace of a 2D dimensional vector space that's in general position. what do I mean general position? Of course, I should really think of this as not being just any 2D dimensional symplectic vector space, but the sum of D copies of a specific one. And that is, by this property I mentioned earlier, h of fq squared, the dth tensor power. And this is the object I want to identify with V. So this is something purely about classical geometry, right? A semi-classical state in a quantum system is a Lagrangian submanifold of the phase space. This is a kind of Lagrangian subspace of a phase space that's especially nice because it's determined, first of all, it's linear, so it's determined by setting linear observables to 0. Second of all, it just happens to be in general position in the sense that it intersects trivially with each of these factors. Intersection with each symplectic subspace is generic. And that's just the sort of semi-classical description of this property of always being an isometric embedding, always having maximal rank that I told you about a moment ago. So this gives you a nice way to think about trying to write down a sort of semi-classical dynamics, albeit one over a finite field, whose quantization in a precise sense is a network of perfect tensors. I think it would be interesting, maybe I'll just close with a few words of outlook because I think my time is drawing to an end. It would be interesting to try and generalize this a bit. Certainly you could think about, for example, Z mod p squared. There's a Heisenberg group for a symplectic free mod or any commutative ring. You could ask about trying to generalize this to try and relate to, for example, ZP valued or even QP valued variables on the nodes of the tree, and to see if some sort of standard notion of pattern will in fact recover Lagrangian spaces of this type or express those results in terms of like a limit of these very, very simple results. I guess I won't have time to come back to the other thing I was mentioning, how to sort of build such a network in a way that plays nicely with the geometry of the tree. But there's some discussion of that in our paper. So I think I'll leave it at that. Thanks for your attention.
Okay, thank you for nice